So, temperature. Have you ever thought about what temperature is? Like, why are some things hot and some things cold? Well, it's kind of hurts your brain if you think about it too hard. It has to do with thermal energy, which is a form of kinetic energy. Remember we talked with the states of matter about how particles of matter, molecules and atoms are not sitting still. They're moving, just like you guys are. You know, you're shifting in your seat, you're taking notes, you're looking around, you're moving. Okay, thermal energy is that motion. Particles of matter are in constant random motion. So the particles in the desktop, even though they seem to be still, they're actually vibrating and wiggling around. The temperature of a substance is a measure of its thermal energy. So if the temperature is higher, the particles have more thermal energy. They are moving more. So the hotter it is, the more random energy, the higher its temperature, the more thermal energy. So one way to remember this is to think about barefoot people on the beach. You go to Pismo and the sand is cool and you're walking barefoot and you just stroll along, you're fine. You go to Reedley Beach and you're walking on the hot sand in your bare feet. Are you going to just stroll along? No, we say you're going to hot foot it to the water, right? You're going to go really quickly because it's hot and it's burning your feet. Hot things, the particles are in faster motion, okay? So that's my stupid analogy for that one. Heat and temperature are not the same thing. Okay. Temperature is a measure of heat, in a way. It's a measure of the thermal energy of the matter. But heat is energy, and it can be transferred or exchanged between objects. And heat transfer is always caused by a difference in temperature. So the heat will transfer from something with higher thermal energy to something with lower thermal energy. It'll go from a high temperature to a low temperature. So if you put an ice cube in a glass of water, well, the water has more thermal energy. It has a higher temperature than the ice cube does. So energy is going to flow from the water into the ice cube. The ice cube is going to warm up. The water is going to cool down. Again, it's this leveling out, going to the lowest common energy. Everything's going to try to level out. So try to remember that heat and temperature are not the same thing. Temperature is something that we measure, and if we measure something, we have to have units. This very, very busy scale slide has a lot of details on it, and I'm going to you can read that at your leisure. And we're going to go look at this temperature conversion scales as a comparison. Okay, so on the left we have the Fahrenheit scale. And this is the one we use, when they say it's going to be 94 degrees today, they mean degrees Fahrenheit. On the Fahrenheit scale, water freezes at 32 degrees and it boils at 212 degrees. Where did they come up with those numbers, right? That's an example, prime example of English system of units, just random numbers, okay? So we kind of remember those because we use them a lot, but, it doesn't really make a lot of sense. So Fahrenheit scale is used in the United States, but not in science. In science, we use the Celsius scale. So the Celsius scale was devised by saying that the freezing point of water is 0 and the boiling point is 100. That sounds a little more like a metric scale, doesn't it? It's like, let's do things in powers of 10. All of these temperature scales were made up by man, okay? There's no intrinsic nature of this. All units we just made up. And so some of them happen to be made up that were less useful, like 212 degrees is the boiling point of water. And others are made up intentionally to be more straightforward. And that's how the metric system works. So the Celsius scale, 100 degrees and 0 degrees. Now the upshot of that is that the difference in temperature here is 180 Fahrenheit degrees and 100 Celsius degrees. And so when we convert between them, we've got adding, subtracting mixed with addition, subtraction. And so that is something that has to be done with a formula, and we'll look at those in a minute. And then over here we have what's called the Kelvin scale. And these numbers may seem random as well. Water freezes at 273.15 Kelvin, and it boils at 373.15 Kelvin. The difference between water boiling and freezing is 100. 100 kelvins, they're not degrees, they're just kelvins. And there's 100 degrees Celsius change here. So a degree Celsius and a Kelvin have the same value, the same temperature difference, they're the same size. The difference between the Celsius scale and the Kelvin scale is where 0 is. So the Kelvin scale was devised on the basis of absolute zero. Absolute zero is a theoretical temperature at which all particle motion ceases. Okay, we actually haven't been able to get to 0 Kelvin. I think they've gotten down to like 0.4 Kelvin. They can get really, really close. I actually don't think it's physically possible to get to 0 Kelvin. But, there's scientists say, if you tell them it's not possible, they'll say, we're going to try to do it anyway and prove you wrong. So people are working on that. The Kelvin scale is used when we talk about gases. We'll talk about gases in a later chapter, but for now we're just going to learn how to do temperature conversions. So here are the two equations, and you should memorize these because we will need to convert between Kelvin and Celsius and between Celsius and Fahrenheit fairly regularly. So the Kelvin temperature conversion is pretty simple. You just take the Celsius temperature and you add 273.15. The trick there is just to remember that number, 273.15. Converting Celsius to Fahrenheit is a little different. We take the Fahrenheit scale and Fahrenheit temperature, subtract 32, which is the freezing point of water, and you take that quantity and divide by 1.8, and that'll get you the Celsius temperature scale. If you have Celsius and you need Fahrenheit, then you have to rearrange that equation. So I think I have an example coming up, yeah. So here's examples. Convert 358 Kelvin to Celsius. I probably didn't leave enough room here. So temperature conversions always need an equation. Always. So the equation we have between Kelvin and Celsius is that Kelvin equals degrees Celsius plus 273.15. And with these equations, this is one of the rare situations where don't bother putting the units into the equation because they're not going to cancel out. So we're starting with Kelvin. We need Celsius. We need this equation to say degrees Celsius equals something. So we're going to rearrange it. So this is adding. So what we'll do is we'll subtract 273.15 from both sides. And we'll end up with degrees Celsius equals Kelvin minus 273.15. If you have issues rearranging equations, please come and talk to me and I'll explain it to you. But I have to assume that everybody can do that. So now we put the number in. I would highly encourage you to rearrange the equation first and then stick the numbers in. If you put the numbers in and then rearrange it, lots of bad things happen, mostly involving getting the answer wrong. So here we put 358 in for the Kelvin temperature, and we're going to subtract 273.15. So 358 minus 273.15 equals. And so the calculator says 84 point, oh, I didn't leave enough room there. 84.85 Kelvin. I'm sorry, it's not Kelvin. Celsius. That's what the calculator says. And then we need to look at significant figures. The rules for subtracting are that you look at the decimal places. What decimal place has the uncertainty? In 358, it's in the ones place, and in 273.15, it's in the hundredths place. The ones place is larger uncertainty, and so we're going to round this off to the ones place, and we're going to call this 85 degrees. Any questions? So the second question is convert 139 degrees Celsius to Fahrenheit. So again, converting temperatures is an equation. So the equation for this, relating these two, is that degrees Celsius equals degrees Fahrenheit minus 32 divided by 1.8. That's an equation that relates the two temperatures, but it's not the equation we need. We're given Celsius, we're trying to find Fahrenheit. We need that equation in terms of Fahrenheit equals something. So we have to rearrange this guy. So there's different ways to think about this. What seems to make the most sense to most students is if there's a fraction in your equation, cross multiply and get rid of the fraction. So when we cross multiply, let's make that pink. We're going to take this side doesn't look like a fraction, and yet it is. You can always just divide something by 1 if you want it to be a fraction. We're going to take these two things and multiply them, and they are going to equal these two things, multiply them. That's what cross multiplication is, if you've forgotten. So we're going to cross multiply and get rid of the fraction. So we get 1.8 times degrees Celsius equals degrees Fahrenheit minus 32. And now we want to get degrees Fahrenheit by itself. If we add 32 to both sides, then we'll be okay. And I'm going to flip it over because I want degrees Fahrenheit over here. 1.8 times degrees Celsius plus 32. Okay, rearranging equations like that is something that we're going to do fairly often in chemistry. And so if you have issues with that, and I suspect that probably at least a third of you do, seek help from a math tutor or come and ask me. I can teach you how to rearrange equations, okay, but I can't do it in class. So you'll have to ask me outside of class. So now we have an equation that we can use. We're going to plug our number in. So degrees Fahrenheit equals 1.8 times the Celsius temperature, which is 139, plus 32. So calculator, 1.8 times 32, times 139 equals plus 32. Get 282.2. Everybody else get that? Always a good idea to do your calculations twice because it's so easy to push the wrong button. So then we have to think about significant figures. This one mixes subtracting with multiplication, and so things can get kind of funny. So we're going to use just kind of a rule of thumb. So you look at the temperature of the original temperature and you ask yourself, in what place is the uncertainty? Oh, 139 degrees, the last digit is the ones place. So I'm going to keep up to the ones place in my answer. I'm not going to, end up with tenths or anything. So I'm going to round this off to 282, and the unit is degrees Fahrenheit. The reason behind that is because the Celsius degree and the Fahrenheit degree are similar in size. One is less than twice than the other, and so they're very similar in size. And so just by converting temperature to a different scale, you should not gain or lose precision in your answer. You shouldn't gain or lose, you shouldn't go from uncertainty in the ones place to uncertainty in the tenths place just because you did some math. Any questions about those examples? I worked the two examples that are more difficult. The other two types of problems, you would just use the equation as it's given and you wouldn't have to rearrange that.